In this video, we will practice using trigonometric identities to rewrite expressions in equivalent forms. This is AP Precalculus Topic 3.12. If you appreciate the content, please give it a like. Here are the identities we learned in the previous video. Pause the screen and practice writing them from memory. No formula sheet will be provided on the AP exam, so you're going to have to know these by heart. Make some flashcards or something. From this point forward, I'm going to assume that you have these memorized. Number 1. Let g of x equal tangent x times secant x. Rewrite g of x as a fraction involving powers of sine x and no other trigonometric functions. Our number 1 strategy is to rewrite everything in terms of sine and cosine. So let's try that now. G of x equals, we know that tangent is equal to sine x over cosine x. And we know that secant x is equivalent to 1 over cosine x. We need to rewrite everything in terms of sine x. Keep that in the back of your mind. For right now, multiplying straight across, we have sine x over cosine squared x. Somehow we need to replace the cosine squared with an expression involving sine x. Quick side lesson. In the previous video, we learned that sine squared theta plus cosine squared theta is equal to 1. This is called the Pythagorean identity. To get cosine squared theta by itself, we subtract sine squared theta from both sides. This gives cosine squared theta is equal to 1 minus sine squared theta. Since cosine squared theta is equal to 1 minus sine squared theta, we can replace cosine squared x with 1 minus sine squared x. And that's it. We have rewritten g of x as a fraction involving powers of sine x and no other trigonometric functions. Number 2. Let h of x equal 1 minus cosine squared x over cosine squared x. Rewrite h of x as an expression involving tangent x and no other trigonometric functions. 1 minus cosine squared x in the numerator reminds me of the Pythagorean identity sine squared x plus cosine squared x is equal to 1. I will get this expression if I subtract cosine squared x from both sides. It would be sine squared x is equal to 1 minus cosine squared x. Therefore, I can substitute sine squared x in place of 1 minus cosine squared. So that gives sine squared x over cosine squared x. This is perfect because we know that sine x over cosine x is tangent x, and sine squared x over cosine squared x will be tangent squared x. We were attempting to rewrite h of x as an expression involving tangent x and no other trigonometric functions, and we've done it. Number 3. Let f of x equal 1 minus secant squared x over sine squared x. Rewrite f of x as an expression involving secant x and no other trigonometric functions. In the previous video, we learned about the Pythagorean identity sine squared x plus cosine squared x is equal to 1. We learned that if you divide both sides by cosine squared x, you get the equivalent form tangent squared x plus 1 is equal to secant squared x. Subtracting tangent squared x from both sides, we get 1 is equal to secant squared x minus tangent squared x. Subtracting secant squared x from both sides, we get 1 minus secant squared x is equal to negative tangent squared x. This was my goal. I see that we have 1 minus secant squared x, and now I have an expression that is equivalent to 1 minus secant squared x. So let's make this substitution. in the numerator I can now write negative tangent squared x. In the denominator we have sine squared x. Of course, tangent squared is sine squared x over cosine squared x. So, you know what, I think I'm going to leave the negative sign out in the middle, which is the same thing. So, tangent squared x is sine squared x over cosine squared x. And in the denominator, I still have my sine squared x. We can think of sine squared x as sine squared x over 1. Now we have sort of a fraction divided by a fraction. When you divide by a fraction, you multiply by the reciprocal. Now we have negative sine squared x over cosine squared x times 1 over sine squared x. Notice that we have sine squared x in the numerator and in the denominator. So these will cancel each other out. Now we have negative 1 over cosine squared x. 1 over cosine is secant, so we can rewrite this as negative secant squared x. This is what we were looking for. Our job was to find an equivalent expression involving secant x and no other trigonometric functions, and that's what we've got. When you work out problems like these, it's important that you show each step individually. Don't try to do more than one step at a time. For example, it would have been tempting to cross out the sine squared x's and convert 1 over cosine squared to secant squared in one step. You have to show one change at a time. So first cancel out the secant squared, then write this, then write negative secant squared. Number 4. Let k of x equal cosecant x times tangent x. Rewrite k of x as an expression involving secant x and no other trigonometric functions. Our number 1 strategy is to rewrite everything in terms of sine and cosine. Let's try that now. Cosecant x is 1 over sine x. And tangent x is sine x over cosine x. I'm noticing that we have sine x in the numerator and the denominator, so these will cancel each other out, leaving behind 1 over cosine x. But 1 over cosine x is the same thing as secant x, and that's what we wanted. Number 5. Let j of x equal secant x times cotangent x times tangent squared x. Rewrite j of x as a fraction involving powers of sine x and no other trigonometric functions. Once again, I'm going to try using our number 1 strategy, which is to rewrite everything in terms of sine and cosine and then sort of see what happens. Secant x is the same as 1 over cosine x. Cotangent x is the same as cosine x over sine x. And tangent squared x is sine squared x over cosine squared x. I see that we have cosine x in the numerator and the denominator, so those are going to cancel each other out. On the next step, the sine x in the denominator will cancel out one of the sine x's in the numerator. We are left with sine x over cosine squared x. We need to continue to rewrite this so that we only have sine x and no other trig functions. We can use the Pythagorean identity to replace cosine squared x with an expression involving sine x. All we have to do is subtract sine squared x from both sides. We get cosine squared x is equal to 1 minus sine squared x. So let's make this substitution. Replacing cosine squared x with 1 minus sine squared x gives us this, an expression involving sin x and no other trig functions. Number 6. Let m of x equal cotangent x times cosine x over cosecant x. Rewrite m of x as a fraction involving powers of cosine x and no other trigonometric functions. I will once again attempt to use my number 1 strategy of rewriting everything in terms of sine and cosine. For example, cotangent x is cosine x divided by sine x. And then we have the cosine x sitting there. That's like cosine x over 1, if you will. And in the denominator, cosecant is 1 over sine x. So what can I do? Multiplying straight across, I have cosine squared x over sine x. 1 over sine x. When you divide by a fraction, you multiply by the reciprocal. So we will have cosine squared x over sine x times sine x over 1. Now we notice that we have a sine x in the numerator and in the denominator. So those are going to cancel each other out, leaving behind cosine squared x. Well, look at that. That's exactly what we wanted. An expression involving powers of cosine x and no other trigonometric functions. Ta-da! The figures show two circles centered at the origin with angle measures alpha and beta respectively in standard position. The terminal ray of angle alpha intersects the circle at point P, and the terminal ray of beta intersects the circle at point Q. The coordinates of P are 4, 3, and the coordinates of Q are 5, 12. Before I get to number 7, 8, and 9, it's usually helpful to write the sine and cosine of alpha and beta. So let's do that first. Sine alpha. We know that sine is y over r, and y is 3, and the radius is 5. The cosine of alpha. Cosine is x over r. So that's going to be 4 over 5. Sine of beta. Y over r is 12 over 13. Cosine of beta. That's x over r, 5 over 13. Now, number 7. The sine of 2 alpha. We have memorized that the sine of 2 alpha is 2 sine alpha cosine alpha. Alright, make sure you have that formula memorized. So we have 2 times, and sine alpha is 3/5. And then cosine alpha is 4/5. Two itself is basically 2 over 1. Multiplying straight across, 2 times 3 is 6, times 4 is 24. And of course 5 times 5 is 25. So this is the answer to number 7. Number 8. The sine of alpha plus beta. Here comes the memorized rule. The pattern goes sine cosine plus cosine sine. So what I mean is the sine of alpha plus beta is sine of alpha cosine of beta plus the cosine of alpha times the sine of beta. Sine cosine plus cosine sine. You have to memorize this. Now it's just a matter of filling in each of these expressions. Sine alpha was 3/5. Cosine beta, 5/13. Cosine alpha, 4/5. Sine beta, 12/13. Okay, I see a common denominator coming, whatever 5 times 13 is. 12 times 5 is 60, so 13 times 5 must be 65. So that's going to be my common denominator. In the numerator, I'm going to have 15 plus 48. The answer to number 8 is 63/65. Number 9. The pattern of the memorized formula for cosine of alpha minus beta is cosine cosine plus sine sine. In other words, the cosine of alpha minus beta is cosine of alpha cosine of beta, sign change, and then sine alpha sine beta. From there, it's just a matter of filling in these expressions. Cosine of alpha was 4/5. So we have 4/5. Cosine of beta is 5/13. And then plus sine alpha is 3/5. And sine beta is 12/13. We just found that 5 times 13 is 65. So once again, we have that common denominator of 65. This time in the numerator, we will have 20 plus 36. So that's the final answer for number 9, 56/65. The next 3 problems are similar to the last 3, so I'm not going to reread the directions. Just like last time, I think it will be helpful if we find the sine and cosine of alpha and beta right from the start. So let's start with the sine of alpha, which is y/r. That's radical 5/3. And we will need the cosine of alpha. That's x/r, so that is -2/3. How about the sine of beta? y/r is radical 7/4, and cosine beta is x/r. That's 3/4. For number 10, there were 3 different versions of the cosine 2 alpha formula. It doesn't matter which one you use for this type of problem. I'm going to use the one that goes cosine squared alpha minus sine squared alpha. So let's see. Cosine alpha is -2/3. So cosine squared alpha is going to be -2/3 squared, and then minus sine squared alpha, so that'll be radical 5/3 squared. Squaring -2/3 gives us 4/9, and squaring radical 5 over 3 gives us 5 over 9. 4 ninths minus 5 ninths is negative 1 ninth. So that is the answer to number 10. Number 11, the pattern of the memorized rule goes sine cosine minus cosine sine. So that's sine of alpha, cosine of beta, minus cosine alpha, sine beta. Now we just need to fill these expressions in. The sine of alpha is radical 5 over 3. The cosine of beta is 3/4. Cosine alpha is negative 2/3. And sine beta is radical 7 over 4. The common denominator is 12. Minus a negative is a plus, so we will have 3 radical 5 plus 2 radical 7. And there's nothing more we can do with this. So that's the answer to number 11. The pattern for the memorized rule for the cosine of alpha plus beta goes cosine cosine minus sine sine. So here we go. Cosine of alpha, cosine of beta, sine change, sine of alpha, sine of beta. The cosine of alpha is negative 2/3. The cosine of beta is 3/4. The sine of alpha is radical 5 over 3. And the sine of beta is radical 7 over 4. I see the common denominator of 12. In the numerator we have negative 6 minus radical 35. And that's all we can do. That's the answer to number 12. On a multiple choice question, you might see it with the negative sign factored out like this. Number 13. Which of the following expressions is equivalent to 4 cosine 2x? We have memorized 3 versions of the cosine 2x formula. Version 1, cosine squared x minus sine squared x. Version 2, 2 cosine squared x minus 1. And version 3, 1 minus 2 sine squared x. Memorize them all. Because we are given 4 times cosine 2x, we need to multiply each of these versions by 4. Version 1 gives 4 cosine squared minus 4 sine squared. That does not match any of the options. Version 2 gives 8 cosine squared x minus 4, which matches option D. Option D is the answer, but let's follow through. If we multiply version 3 by 4, we get 4 minus 8 sine squared x. That's similar to option C, but we have a minus, and here it's a plus. Number 14. Which of the following expressions is equivalent to the quantity sine x plus cosine x squared? Be careful. A common mistake is to think that you can just square each one of these individually and get sine squared x plus cosine squared x. This is bad algebra. If this were possible, sure, we would get 1 and the answer would be A. But like I said, this is bad algebra. The answer is not going to be A. To square a binomial, you have to multiply it by itself. You have to FOIL this, first, outer, inner, last. Or you can think of it as doing the distributive property twice. Sine x times sine x is sine squared x. But then you have to multiply sine x times cosine x. So that'll be plus sine cosine. Sine x cosine x. But then you have to multiply cosine x times sine x. That's going to be another sine x cosine x. However, since we have two of them, instead of writing it twice, we can just write 2 sine x cosine x. And finally, we have to multiply cosine x times cosine x, which gives us cosine squared x. So this is what we have for a brief moment. Notice that we do have sine squared x plus cosine squared x. So if we rewrite the order here to make it clear, we have sine squared x plus cosine squared x plus 2 sine x cosine x. Now, sine squared x plus cosine squared x does give us 1. That's our Pythagorean identity at work. So we have 1 plus 2 sine x cosine x. This is a double angle identity. This part is the sine of 2x. So putting it all together, we have 1 plus the sine of 2x. So the answer is D. Number 15. Where cosine x does not equal 0, which of the following is equivalent to cosine squared x minus 1 over cosine squared x? We remember the Pythagorean identity sine squared x plus cosine squared x equals 1. We are also familiar with the version that we get if we subtract cosine squared from both sides. Sine squared x is equal to 1 minus cosine squared x. I'm mentioning this because I see cosine squared x minus 1 in the numerator, and that reminds me of 1 minus cosine squared x, but they're sort of backwards. So I need to flip this around in some way to make it match. Addition is commutative, so I can switch these around no problem and put the negative 1 in the front and the cosine squared second. If I factor out the negative sign outside of parentheses, I get negative and then 1 minus cosine squared x. That's what I was shooting for. I can now make the substitution. 1 minus cosine squared x is equivalent to sine squared x. So I'm going to have the negative here in the front, but then I will have the sine squared x all over cosine squared x. So I'm looking at the options. The answer will not be A because it's almost this, but we have a negative, which this does not have. So that is out. I see the options of cotangent squared and negative tangent squared. Well, sine squared x over cosine squared x is tangent squared x. And we do have this negative sign in the front. So this is equivalent to negative tangent squared x. So the answer is C. Number 16. Which of the following expressions is equivalent to the quantity 1 plus cotangent squared x times sine squared x? We learned 3 versions of the Pythagorean identity. Sine squared x plus cosine squared x equals 1. Tangent squared x plus 1 is equal to secant squared x. And 1 plus cotangent squared x is equal to cosecant squared x. And right here I see 1 plus cotangent squared x. So that will be equivalent to cosecant squared x. So this expression will then become cosecant squared x times sine squared x. So what is this equivalent to? Let's use our number 1 strategy of rewriting everything in terms of sine and cosine. Cosecant squared is 1 over sine squared x. So I have 1 over sine squared x times sine squared x. Well, it looks like the sine squared x in the numerator and the one in the denominator will cancel each other out, leaving just 1. So the answer is A. Number 17. Which of the following expressions is equivalent to 3 times sine of 2x? We have learned a memorized formula for the sine of 2x, and that is 2 sine x cosine x. Since we are multiplying by this 3 in the front, we will have 6 times sine x cosine x. So let's see. Well, the answer is C. Number 18. Which of the following expressions is equivalent to cosine 5 pi over 9 cosine 3 pi over 9 minus sine 5 pi over 9 sine 3 pi over 9? Notice the pattern cosine cosine minus sine sine. That matches the pattern for the identity cosine A plus B, which equals the cosine of A times the cosine of B minus, notice the sign change, the sine of A times the sine of B. Cosine cosine minus sine sine. As we match up the factors, we see that A is 5 pi over 9 and B is 3 pi over 9. So we can work backwards and write an equivalent expression in the form cosine of A plus B, where A is 5 pi over 9 and B is 3 pi over 9. These are fractions with like denominators, so we can combine them into a single fraction using the common denominator. 5 pi plus 3 pi is 8 pi. So we have 8 pi over 9. So the answer is B. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.